Hi everyone, welcome to the last part of LU3, Learning Unit 3, which is Gravimetric Analysis. Today I'm going to share with you about common ion effect and also volatilization gravimetry and some of the calculations involved in gravimetric analysis. Now, if an excess of sodium sulfate is added to barium chloride solution, the reaction should be like in the slide. BaCl2 plus Na2SO4. We have the product BaSO4 and 2NaCl. Now, BaSO4 is poorly dissociated while sodium sulfate is strongly dissociated. So when you compare both of the species, Na2SO4, it will tend to dissociate more compared to the BaSO4. So in this case, BaSO4 will dissociate into Ba2 plus and sulfate, which is poorly dissociated, and sodium sulfate will dissociate into Na2 plus, Na plus and sulfate, which is strongly dissociated. So due to common ion, the poor dissociation of BaSO4 is further decreased, and the solubility of BaSO4 is decreased. Okay, in this case, the formation of Na2SO4 will be more visible compared to BaSO4. Okay, so BaSO4 is having lower solubility and the dissociation is further decreased. For example, here you have 10 ml of 0.2 molar silver nitrate added to 10 ml of 0.1 molar NaCl. So if we want to calculate the concentration of chloride remaining in the solution at equilibrium and the solubility of AgCl, we can use the following technique. The final volume after reaction between AgNO3 and NaCl is 20 ml because we have 10 ml of AgNO3 and we have another 10 ml of NaCl. So we have the final volume 10 plus 10, 20 ml. Now, calculate the millimoles of Ag plus added. How do you calculate millimoles? We know that moles equal to MV, molarity, times volume in liter. So millimole is MV as well, but M is molarity and V is volume in milliliter. So we have here 0.2 molar times 10 mil of AgNO3, which contributes to Ag plus ion. So we have 2 millimole of Ag plus. And we calculate the millimoles of chloride. This is the millimole of chloride taken. We have M, 0.1 molar, and we have 10 mil of NaCl. So we have 0.1 times 10, which is 1 millimole of chloride ion. So from there, we have millimole of AgCl form. The limiting reactant here is the Cl, chloride ion, because we have 1 millimole here. And the millimole of AgCl form should be 1 millimole as well. Okay, I repeat, millimoles of chloride here is 1 millimole. Okay, because chloride is the limiting reactants, so we have millimole of AgCl form, which will be 1 millimole as well. So we calculate the millimole of excess Ag plus. So we have 2 millimole minus 1 millimole, 2 millimole from Ag plus added and 1 millimole from chloride taken. So 2 minus 1 is it's 1 millimole. So we have 1 millimole excess of Ag plus, and we have excess concentration of Ag plus. How do we calculate excess concentration? We go back to the formula N, which is mole, equal to M, molarity, and V, volume in liter. So here we're going to use information all in millimole and milliliter. So you can use M equal to N, millimole, divided by V, volume in milliliter. So this is N, the number of mole, which is 1 millimole. You get it from here, the calculation of excess Ag plus. And 20 mil is the total volume of total volume after AgNO3 and NaCl reacted. All right, so you have N divided by V. You have 0.05 molar. Then here, from there you can calculate the solubility of AgCl. 0.05 times molarity of Cl, chloride ion here, is equal to 1 times 10 to the power of negative 10. This number, it comes from the solubility product of AgCl. Okay, so 0.05 is Ag. Now we have to find Cl. So this is KSP for AgCl. Okay, so here we get solubility of the chloride ion 2 times 10 to the power of negative 9 molar. Now we move to volatilization gravimetry. Volatilization gravimetry is a decomposition of solid sample through thermal or chemical treatment. Okay, so from the thermal or chemical treatment, the solid sample will yield volatile products, and the volatile products of the decomposition reaction may be trapped and weighed, and we get the mass of our product, or residue remaining after complete decomposition may be weighed. So this is what we call indirect analysis. For direct analysis, we trap the volatile product and we weigh the volatile product. So this is called direct analysis. And another analysis is indirect analysis, where we have the residue remaining after complete decomposition that we weighed, and then from the calculation, we can calculate how much is the mass of our volatile product. So this is what we call indirect analysis. So thermogravimetry is an example of volatilization gravimetry. If you look at the example here, this is an apparatus for determining the sodium hydrogen carbonate content of antacid tablets by a gravimetric volatilization procedure. So if you look at here, we have nitrogen as the carrier gas, and we have a reaction mixture containing bicarbonate and sulfuric acid. What happens when bicarbonate and sulfuric acid react is that they will release water vapor and also carbon dioxide. So in this case, we will pass through the water vapor and carbon dioxide through a drying tube containing CaSO4. Why we want to pass through the water vapor and CO2 through the drying tube is because we want to remove the water vapor and leave only CO2 after it has passed through the drying tube. Why? Because we want to quantify CO2 mass. Okay, so when we have CO2 here, after drying of the moisture, it goes through another tube, which NaOH on non-fibrous silicate and CaSO4. So what happened here is CO2 react with NaOH to form sodium carbonate and water. Okay, so from here you can have and you can calculate your volatile product, which is the mass of CO2. All right. In volatilization gravimetry, it requires the product of decomposition reaction to be known. Okay, it requires the product of decomposition reaction to be known. If we look at the example here, we want the mass of our decomposition reaction, which is CO2, to be known. Okay, so this is for the case of reaction between bicarbonate and sulfuric acid. All right, now we go back to the slide here. Organic compound, which is accomplished through combustion. The products are gases such as carbon dioxide, water, and nitrogen. But if you have inorganic compound, if you put them under thermal decomposition, the product may depend on the decomposition temperature. For example, taking one compound here, CaC2O4, H2O, at different temperature, we lose different species. Let's say at temperature between 100 degrees Celsius and 250 degrees Celsius, normally the loss is on water content, which is H2O. So the residue will become Ca2O4, and at temperature 400 to 500 degree, the loss will be carbon monoxide. So the residue living after the gravimetric analysis is CaCO3. And at higher temperature, let's say 700 to 850 degrees Celsius, we will lose CO2, which cause us to have the residue in the form of CaO. It doesn't matter what is the final composition of your reaction. You might want to do different temperature decomposition because you want the final product to be different. For example, you want to determine CaO, so you use this temperature. If you want to determine CaCO3, you have to use this temperature. So it depends on what you are looking for during volatilization gravimetric analysis. For volatilization gravimetry, we depending on the equipment. At the beginning of this lecture, just now I mentioned about subjecting your sample to thermal or chemical treatment. So your equipment may be simple and may be complex. These are some examples of simple experimental design, whether we use burner or we use furnace. Okay, furnace is normally used for volatilization gravimetric in most laboratories. So in this case, volatile products are vented to the atmosphere and the solid residue are weighted using analytical balance. Okay, so if we want to determine the volatile content of our product, of our reaction, we have to minus, okay, the solid residue that we have weighed. Okay, and another option for volatilization gravimetric is to have a complex design where we have constant temperature decomposition or combustion followed by trapping and weighing of volatilized gases, as we have in our previous slides on reaction between bicarbonate and also sulfuric acid. Just now, we have volatilized gases trapped in drying tube, and also some another tube which contain chemicals and convert our product into something else that we can quantify, we can calculate. Okay, normally it is conducted in a closed container, and volatilized gases carried by a purged gas stream. In our case just now, in the previous example that I've shown you, the carrier gas was nitrogen. Okay, the volatilized gases was carried by a purged gas stream through one or more selective adsorbent traps. So these are examples of a complex design. for volatilization gravimetry. Right. Volatilization gravimetry can be used for quantitative application. Remember, quantitative application is for us to determine the value of our analyte, how much we have our analyte in our sample. All right. Um, let's say we have inorganic analysis or direct analysis of inorganic analysis. For example, we want to determine inorganic ash content of organic materials such as polymer and paper. Okay, let's say we have our sample polymer and paper. So what we want to do here is we want to determine the inorganic ash content of our material. So what we do, we can weigh the sample, the polymer and paper sample can be weighed in crucible, and we remove the organic matter from polymer and paper through combustion. Okay, we put them into muffle furnace. We conduct combustion process. So during the combustion process, the organic part of the sample is removed through the combustion process. So the residue is then heated to a constant weight using either burner or oven. Normally we use oven. Okay. So this is another example of quantitative application of volatilization gravimetry. Um, let's say we have indirect analysis of inorganic analysis. So it's based on the weight of the residue remaining after volatilization. So in this case, we do not measure the mass of our volatiles. We did not take the volatiles and we measure the mass, but in this case, we take the mass of the residue and then we do some calculation to determine the mass of our volatiles. Okay. In this case, let's say we are determining moisture in a variety of products. Okay. We dry the pre-weight sample with an infrared lamp or low temperature oven. So during drying, we determine the mass of our residue and then we do some calculation to find out what are the mass of our volatiles. Another application for volatilization gravimetry is on the organic analysis, most of the time called elemental analysis. In this case, normally the elemental analysis is on the determination of carbon, hydrogen, nitrogen, sulfur, and oxygen. Okay, so in this case, we burn our sample in the stream of oxygen. So the end product would be carbon dioxide and water. So this combustion product, they are passed through a pre-weight tubes. Remember just now I show you a schematic diagram of volatilization gravimetry apparatus using drying tubes. So you can imagine doing the same thing in this case. So these combustion products are passed through the pre-weight tubes containing appropriate adsorbents. So the purpose of this adsorbent is to take away moisture, and then you can get the mass of carbon dioxide. Okay. And if you want to determine how much H you have, you would have to put other adsorbents which can trap other things except H, okay, H2 or hydrogen gas. Okay, so we will have an increase in the mass of tubes and we do some calculation based on the mass increase. Let's take a look at this quantitative application calculation. Let's say we have 101.3 milligram of sample in an organic tube, which is burned in pure oxygen. So when we burn in pure oxygen, it's combustion process, and the adsorbent tube used to trap CO2 increase in mass by 167.6 milligram. Okay, determine the percent weight to weight carbon in the sample. So this is an example for elemental analysis. Okay. First things first, we have here the comparison of moles between carbon and carbon dioxide. So in this case, moles of carbon is equal to the moles of carbon dioxide. So from here, you can determine the mass of carbon based on the mass of CO2 trapped. Okay, here if you look at the increase in the question, it shows that the increase in mass of the adsorbent tube used is 167.6 milligram, meaning to say that when there is an increase of mass by this number, it means that this is the mass of CO2 trapped in the adsorbent tube. All right, so from this question, you know that you already have the mass of CO2. You can have from the periodic table the formula mass for C and CO2 as well. So from there, you know what is the mass for carbon. Okay, but in this question, we don't only want to know the mass of carbon, we want to determine the weight percentage of carbon in the sample. So what we do is we divide the mass of carbon with the mass of our sample and times with 100% to get the percentage of carbon in the sample. Okay, this is another exercise. It should be able to be solved by using the same approach just now. We have this much sample 1013 milligram of sample of organic compound, and the adsorbent tube used to trap water. Just now we want to determine CO2, and now we want to determine water. Okay, increase in mass by 13.7 milligram. So again, when the adsorbent tube increases in mass by this much, so we know that this much is the mass of our analyte. What is our analyte here? H2O. Okay. So from here, we know that 2 moles H is equal to 1 mole of H2O. So we use the same approach. We know the mass of water, formula mass of water, atomic mass of hydrogen. So from here, we can have the mass of hydrogen. And then we can calculate the percentage of hydrogen in sample by dividing the mass of hydrogen to the mass of sample times 100%. Okay, so this is going to be an exercise that you can do. A sample of slag from a blast furnace is analyzed for SiO2 by decomposing a 0.5003 gram sample with hydrochloric acid, leaving a residue with mass of 0.1414 gram. So after treating with this kind of acid and evaporating the volatile SiF4, a residue with a mass of 0.0183 gram remains. Determine the percentage weight to weight SiO2 in the sample. Okay, for this case, what you do is you can get the mass of SiO2. Okay, how do you get the mass of SiO2? By having the residue of SiO2, which is 0.1414 minus 0.0183 gram, which is a residue after volatilization. Okay, so this is before volatilization and this is after volatilization. So you get the mass of SiO2 volatiles, which is 0.1231. Okay, so how do you determine the percentage weight to weight? You already know the gram of SiO2, which is 0.1231 divided by the gram of sample. Okay, the original sample is 0.5003 gram. times 100%, so you get 24.6%. Okay. Now we move to particulate gravimetry. Analyte is present in a form that may be readily separated from its solid, liquid, or gas metric. So analyte is separated by two approaches. For example, we have filtration and we have extraction. Remember, we have done experiment 2 on determination of suspended solid, total solid, and dissolved solid in water sample. So that's a part of particulate gravimetric principles which has been applied in that experiment. So in this case, the analyte is present in a form that may be readily separated from its solid, liquid, or gas metric. All we have to do is just to separate and take them out using either filtration process or extraction process. Okay. In filtration process, liquid samples are filtered through an appropriate filtering medium, either by gravity or suction. Okay, and the choice of filtering medium depends on the size of the particulate and the sample's matrix. Meaning to say that you choose your filter paper or your filtering medium depends on the size of your particulate. So these are some of the examples of filter paper that you can choose. Let's say you have a uh, particulate size, okay, which range from 30 micron to 3 micron. So you can use cellulose fiber filter paper. What about glass fiber filter? Okay, glass fiber filter caters for particulate with pore size range between 2.4 micron to 0.3 micron. If you look here, this is finer compared to the cellulose fiber filter paper. Okay, and membrane filter is for particulate with pore size range between 5 micron to 0.1 micron. If you look at here, different type of filter will have different particulate pore size range that they can cater. Okay, so the choice is depending on the type of your sample and the pore size range of your particulate involved in the filtration process. Okay, these are some example of filtration process. Let's say you have solid aerosol particulates in gas sample. You can filter them using either a single or multiple stage filter system. So in a single stage filter system, the gas is passed through a single filter, retaining particles larger than the filter's pore size. Okay, so in a multiple stage system, we have a series of filtering units that is used to separate the particles by size. Okay, so you have two options for filtration of gas. What is the quantitative application of particulate gravimetry? Particulate gravimetry is common in environmental analysis of water, air, and soil sample because we already have our analyte ready to be separated from our samples. Let's say the suspended solid in water, dissolved solid in water, and also total solid in water. Okay. Let's say we have analysis for suspended solid in water samples. Filter an appropriate volume of well-mixed sample through a glass fiber filter and dry the filter to constant wet at 103 to 105 degrees Celsius. So this has been done in experiment 2. Okay. And then number 2, another example is grain size distribution for sediments and soil. Grain size distribution, or we call it sometimes particle size distribution, PSD, okay, for sediments and soil, which are used to determine the amount of sand, silt, and clay present in your sample. So the grain size boundaries for sand silt is 1 to 16 millimeter, and for silt clay is 1 to 256 millimeter. Okay, so these are two of the quantitative application of particulate gravimetric analysis. Of course, there are many more, but these are the common applications of particulate gravimetry. Let's look at the quantitative calculation. You have done some of this type of calculation for experiment 2 again. And then let's see here, we have a 200 ml sample of water, which was filtered through a pre-wet glass fiber filter. After drying to constant weight at 105 degrees Celsius, the filter was found to have increased in mass by 48.2 milligram. Okay, so now here the filter was found to have increase in mass. So the increase in mass here is the mass of your analyte, okay, which is 48.2. Determine the total suspended solid for the sample in ppm. So you have 48.2 milligram, which is the mass of your suspended solid, your analyte divided by the volume of your water sample. Okay, whether you express your answer in milligram per liter or in ppm, but in this case, you are required to express your answer in ppm. So you should answer in ppm. Okay, so this is another example. Concentration of airborne particulates in an industrial workplace was determined by this method mentioned in the question. The air was sampled for 20 minutes at this rate, and at the end of the sampling period, the glass fiber filter was found to have increased in mass. So whenever you have the word increase in mass by something, so this something is the mass of the analyte collected through that process. Okay, so what is the concentration of particulates in the air sample? So you have the flow of your sampling 75 meter cube per hour. So you can calculate how much sample that you can collect in 20 minutes. Okay, because in this question, it has mentioned that the air was sampled for 20 minutes. So you calculate in 20 minutes how much sample you will have, which is 25,000 liter. Okay, so the concentration of the particulates in the air sample is the mass increase of your filter, glass fiber filter just now, the increase in mass. So this is your mass of analyte, and this is the mass of your sample taken within 20 minutes, which is 25,000 liter. So this is your answer. Okay. All right. Another type of particulate gravimetric analysis is through extraction process. Normally, it is used for analyte of the gas phase, solutes, and poorly filterable solids. It uses suitable solvent for extracting the analyte. After extraction, the solvent can be evaporated and the mass of the extracted analyte can be determined. Okay, so in the case of using extraction method in particulate gravimetric analysis, it's normally for the gas phase type of analyte, the solutes, and poorly filterable solids. Okay, so in extraction, you remember we use suitable solvent, and after extractions, the solvent can be removed or can be evaporated from the mass of the extracted analyte. Okay, so the analyte can be determined indirectly by measuring the change in the sample mass after extracting the analyte. Okay, so that's the end of learning unit 3. I hope if you have any questions, you can ask me. And please try to do all the study questions for Learning Unit 3 and the class activity for Learning Unit 3. And thank you.